Today's lecture will be given by Professor Byrd from National Cancer Institute. It's a great privilege to welcome you, Professor. The floor is yours.
Well, thank you very much. I need to thank both Stefan Jurga for the kind invitation to come, and also Bernard Blumish, who was here earlier this week. Bernard and I go back a long ways. We shared a lot of interactions at the ENC and various things. And part of the reason for me being here is to, and it's wonderful to be here, I also participated at an Ampere summer school, very much like this, but this was about, I hate to say this, 35 years ago in Austria, in Graz, and that one was organized by Oleg Chardetsky, but it was similar. It had a nice, good feel, lots of young people, and we had a very diverse program as well. It was very interesting. That was in the days when I was in Canada, and it's wonderful to see old colleagues, Alex Mackay and Rod Wasselushin and stuff. So this is really kind of a homecoming scientifically, as well as a chance to talk to you about a couple of topics today. And the first topic is one about a colleague of ours who is no longer with us, Ida Littman, who is an Estonian, a scientist. I would like to tell you a little bit about him because his involvement in the NMR community and the scientific community of Eastern Europe is really quite important, and his role in the Ampere Society as well. And then I'd like to spend the rest of my time talking to you about some new approaches to analyzing relaxation experiments. A little bit of a twist on relaxation, and we'll go through that as well. Let's see if I can figure out how to turn this. So, this is Enda Littman. He passed away about 11 months ago. Now, it's a little interesting. You have no question wondering whether I'm Estonian with my accent. But it turns out that I was related to Endel through spouses twice fold. His wife was the cousin of my wife's aunt, if we can figure out how many cousins removed that is. But the thing about this was really quite intriguing. As I was getting going in my career, and this actually turned out to be in Canada, my wife is a first-generation Canadian of Estonian parents. And so I got to know the Estonian community, and in one of the discussions they were trying to, most of them were not scientists, and they were trying to explain who this crazy American living in Canada that was seeing this nice young Estonian woman, and they said, oh, but he's a scientist. Well, oh gosh, let's hope he's not like that other scientist. So my Estonian was not very good, but I could tell when I was being talked about, right? And so I said, well, who is the other crazy Estonian scientist? And they said, Enda Littman. I couldn't believe it, because this was in the late 70s. I actually knew the name, and I'll tell you how I knew the name, but I was like, it can't be the same one. And I'm going, how many Littmans are there in Estonia that do NMR? Because that's the way I knew of it. And it turns out, of course, that it was, in fact, the Enda Littman. And I had the great pleasure of getting to know him in the 80s. And I'll tell you how that came about, because it was the time when he was coming to the US, and it's an intriguing story. But Endel was, he was a fun guy, and I got to know him. I got to visit and talk to him. He looks very calm and timid here, but he was a very piercing intellect and a challenge to talk to, but a wonderful man. I give you, his record is really just outstanding. Just to give you some highlights, the family shared with me so much, but he was born in 1930 in Tartu, Estonia, and his father was a professor of biology. Quite interesting, because Endel became a physicist, but yet always kept a very intriguing interest in biology. He used to quiz me more than I could ever tell, because I trained in physical chemistry. But he went through the institutions in Tallinn primarily, and he actually got a Doctor of Science from Moscow, the Institute of Chemical Physics. What's more important is what he did with his education. And he started out in the late 50s as he was finishing his degree. He was teaching at this is the Tallinn Institute of Technology. And he never was able to be a faculty member, because even if you ever met Endel later in life, you know, he was not timid about his opinions. He was very outspoken. And so he was not going to make faculty do political things. But he rapidly moved into the Estonian Academy of Sciences and held very prominent positions and helped develop the Estonian Academy of Science, the Institute of Chemical and Biophysics. and had very profound impacts. But I think one of the things that made him stand out, the way I came to know him, and I think the way he impacted all of us in science, was his foreign exchange. He started early in the 60s with exchange programs into Finland at Uppsala University. He began interacting with Brooker, and then these series of meetings that he organized reflected how much he viewed science internationally and involving with them. So there was an international symposium on chemically induced dynamic nuclear polarization. Now, nuclear polarization is a big thing now, and actually in those days, in the 70s, if you read that literature, Rob Kapteyn was known for a lot of this work in biology, but as I discovered, Endel was very involved in the small molecule and chemical reactions in doing this. And in that period, he also was able, finally, with a lot of pressure on the government at the time, to make foreign visits. And particularly, he got to know Alex Pines, John Law, Nino Iannone at IBM. And Alex has told me some great stories about it that I will share with you around coffee. But he also then became involved in the broader European community and helped organize a Congress of Molecular Spectroscopy in Tallinn. And then one that really stands out and is appropriate for the organizers of this meeting, he organized the 20th Ampere Congress in Tallinn in 1978. And in this, there were the pioneers of solid-state NMR and Endel's group, and they interacted, and it was really quite a special time. Some milestones: he actually built the first NMR spectrometers in Estonia and started chemical and structural applications. They were very prominent in developing high-speed MAS systems that were patented in 10 countries, but there were some political issues about money. He was very involved in developing computational resources, and one thing that was really interesting, and this involved his son as well, Jaak, they actually were involved in getting the internet started in Estonia, and many of you may know that Skype was an Estonian development, and all of this internet stuff was driven a lot by the Netherlands. He has a great number of honors here. I don't want to take too much time and go over this, but really it was quite, he won the Ampere Prize in 1994. He was chosen as one of the most important Estonians in the 20th century, and lifetime achievement medals from the Estonian Republic. Now, the thing that was interesting, he was a fantastic scientist, but he also was seamlessly engaged in political activities as well. And particularly in the 80s, when I got to meet him personally and interact with him, when he would come to the US and stayed with us in Washington, I didn't appreciate what he was doing then, but he was actually going to the Library of Congress and researching documents that became seminal in the subsequent years of what happened in Estonia. I just tell you briefly, he did sort of a Trojan horse approach with the government at that time the Soviet Union, and he became a member of the Congress of People's Deputies. And this was in doing environmental studies about mining in Estonia. It was kind of the guise of this, but it was really going to change the influence of the Soviet Union in Estonia and prevent its becoming independent. And through this, he actually worked, and I'll show you in another slide, what he helped do to break a very important pact there. And that was doing research in the US and in many Western countries. But he then served in the government. He was a member of 3 different federal governments in Estonia. And so when he passed away, his obituary was talking about all his political activities and said very little about his science, which is really amazing. So just to give you a little bit of a light, this was the first spectrometer that was built in Tallinn with an iron magnet that was almost homemade as well. And the second one involved collaborations with JOL. They started bringing in other components. And with this equipment, they started both solution and solid-state NMR. And in the 70s, early 70s, we're doing these dynamic nuclear polarization experiments where you could see both emissions and absorptions, and both in carbon and nitrogen spectra. So this was in the 70s, very early days. Very cutting edge, equal to everything going on into the West. And of course, this is a picture from the 20th Ampere Congress in Tallinn in 1978, and meeting with Raymond Andrew. And this is when they were getting going, all the high-speed magic angle spinning and this sort of stuff. Now, some of you may know one of his famous colleagues, August Samuelsson, who has been a very key developer of high-speed MAS and is to this day. And then this was in the later years in some of his political meetings with one of the presidents of Estonia. I just want to say, highlight a couple of papers here and what they did, which was really quite intriguing. This was their starting to get involved in solid state NMR in 1978. I found this kind of interesting. They realized even very early on, before some of the other groups in the West that knew about this, that they could actually extract anisotropy values by slight changes in the magic angle. And this was when Schaefer and Stageful were active, and all of this work was going on at the same time. With Ago Samuelson, they also started, they were involved very early on, this is in 81, looking at quadrupolar nuclei and rotating solids. And let me just, I'm going to kind of wind up this up, but I want to give tribute to Endo. This was when he served in the People's Congress in Moscow, and the goal that he had was to sort of expose the secret arrangement from 1939, the Molotov-Ribbentrop Pact, which actually led to the annexing of the Baltic states into what became the Soviet Union. And he became, say, a contestant with Gorbachev. But they actually worked out, and through all of these actions, it led to the overturning this pact, so it disowned this annexing. And then, as we all know, in the late 80s, as the Soviet Union disbanded, Endel also worked with Yeltsin in this, and they reached this agreement where the Baltics would go free. But I would really like to say that he was a very charming guy around family, and this is a nicer smile on him. It's much more the way he could be remembered. But he was a pioneer in NMR. He was committed to all the causes, but he was uncompromising and fiercely competitive. But it was a challenge always to explain what you did to him. And even up through, since 2000 to 2010, he was working at CERN doing high energy physics. I mean, he was seamless between politics and science, and I think did a great thing for Estonian scientists and all in the Eastern countries. So I was pleased to know him and to share a little bit of that with you. Okay, so let me spend the rest of my time telling you a little bit about the science that we do in my lab. And I'm not going to talk so much about the biology. I'm going to show you just a couple of pictures. I want to talk about just looking at relaxation experiments and dynamics. Some of the systems we work on are multi-component protein complexes. This is one from the ubiquitin pathway. It actually, in cartoon form, involves various multiple domains, and it interacts with the membrane. As Alex McKay will remember, I used to work on membranes once when I was in Canada, and life is coming back. I'm starting to work at systems that now embed and associate with membranes. And we also work on another system, ARF1 and ASAP1. These are GTPase activating proteins, and they interact with membranes. And we actually use membrane mimetics, these small nanodiscs. We look at domains interacting with the surface. But I show you this only to emphasize the fact that in biology, in these complicated systems, we can look at them in cartoons, but we're always looking at how these various pieces work together, not unlike many of the systems you've heard about this week, and interactions between molecules and the real power that NMR spectroscopy has to look at that. And I want to focus, while we do structures and a variety of things using NMR, today I want to talk just about conformational and exchange dynamics, these time-dependent phenomena. And I think I wrote in my abstract, one of the beauties about NMR is it's such a robust theory. And fortunately, except in certain strong coupled cases in solids, it can be treated as a weakly coupled quantum mechanical system. So that gives us a robust theory to analyze this. We get into trouble sometimes, and I'll show you, the whole point of this second part is to show you that you can get entangled, but there are ways out. But understanding conformational exchange and dynamics or interconversion between states is very important. This can be just as simple as going from state A to state B, or it may be the binding of two molecules, A plus B, giving you a complex. And we would like to understand this both temporally and structurally, because that's going to tell us something about function. NMR is a fantastic tool for this. If we look at molecular events, there's all kinds of things that happen. In the time scale of picoseconds and nanoseconds, we have vibrations, librations of bonds, side chain rotations. As we extend into the microsecond to millisecond to second domain, this is where catalysis occurs by enzymes. In the biological case, there's binding of two molecules together, allosteric recognition. And the interesting thing is that the NMR spectroscopy is very robust. We have methods across all of these time scales to look at this.
relaxation rates in the lattice frame and rotating frame, the transverse frame, NOEs. We have Carper-Cell Meidenbill type spin echo experiments, exchange, rotating frame relaxation, residual dipole coupling. We have all of these that can reflect on time scales, not just give us a specific chemical shift or something. And it's this region where many biological processes are catalyzed and recognition, both molecular recognition through allostery and chemical reactivity that drives biology. So it's very interesting over the last 2 or 3 decades as things have occurred in structural biology. We focus so much on how to maintain, to develop three-dimensional structures and use this to interpret it. And a bunch of the slides here is a mixture between my colleague Louis Kay, who many of you will know of, and I stole some of these from him the last couple of days when he was in Washington for a symposium honoring our colleague Ad Back. This is one of Lewis's, and he likes to say, we spent all our time trying to understand the low energy state, and we're probably doing the wrong thing. Is that we really need these next step up, a higher energy state that may be as simple as an unfolded state here or any other motion, because this is part of recognition and regulation. If you only interact with the ground state, then you don't have any control for regulation. But if you now regulate what this barrier is, so this is a lowly populated state, this may actually be the functional one. Okay? And Lewis drives a lot of his recent work in the last 10 or 15 years about that. But it's really the dynamics and structure of these lowly populated states, the high energy state. And that may be what mediates folding or misfolding of states. Misfolding can give you an unfolded protein, or it can even give you fibrils that lead to neurodegenerative diseases, etc. And enzyme catalysis may take place from this lower populated excited state. And the binding to ligands actually may occur at sites that aren't exposed in the low energy state. And this drives a lot of the actual biology that we do in my lab. I'm not going to go into details of biology. I want to talk about how we think about this and how we look at this. Okay? So the thing is that this interconversion between these states may be on the microsecond or millisecond time scale. And these states may be very lowly populated, less than 1% or a couple of percent. Okay? And the thing is how do we learn about this? If this is truly the active state, inferences that we make here are in fact either incorrect or misdirected, and it takes us a while before we find this out. And Lewis has dedicated a lot of work, as many others have, to do this. And how do we get that without totally changing the system? Can we see this in situ? So let's talk just about chemical exchange, or two-side exchange. And this is just classic changing the rate at which two states change from A to B. There's two lines. This is the line in state A and the line in state B. And if the rate is, if it's not exchanging and you have a 50% population, we know you get two lines. As you start hopping between these two, first they broaden, then they coalesce, and then it shows as a single line. This is something we learned early in NMR. And of course, if it's a unequal weighting, then this occurs at the population weighted average between these two. You see them broaden, they coalesce, and then they come together as this rate changes. Okay? So that's fine, although this is starting to tell you the problem. If this is now 1%, this is barely shifted and you can't tell it's there, but it may be very, very important. Okay? What we're used to seeing often in NMR is titrating two species and you see something change. And this is watching this population weighted state move between the two positions as it goes along. So this is very common. But it may be that our ground state is something that we can't see. It's only a few percent. And let's say that it's changing at 50 per second and the population is 1.5%, then this rate is 0.75 for the ground state to the excited state. Okay? So this has been studied. There's a wealth of literature on this using the Carper-Cell Meidenbill experiments. And so you can measure this impact of the low state on the bigger state. Okay, and how does this happen? Well, initially there's line drawing in the highly populated state, if we're going over this barrier to state B, but this state is too weak. We can't see it if it's slow exchange, and if it's fast exchange, we only pick it up here. Okay? So the question is, this chemical shift difference becomes very important, and that tells us something about the different structures. So we would like to understand what the chemical shift is, and the rate of interconversion. So we like to be able to measure chemical shifts in the invisible state where the exchange rate is in the hundreds to thousands of seconds. So let me give you just a conceptual view, and again, I borrowed these from Lewis and Tony Mittermeier about what happens in the NMR experiment. If you have two states, in this case they're equally populated, and if we consider an offset here, so these frequencies in the rotating frame, the cyan state is walking pretty slowly, and the red state is a runner, okay, and that's fine. But now if there's only a small number, of these, you couldn't see it, you'd only see this time, okay? So how can we detect the presence of this if this is at a low state? Well, we take advantage of this spin echo introduced by Erwin Hahn at Berkeley many years ago in the very early stages of NMR. And if we consider that if we start after an initial pulse, their spins are moving and we let them walk for a time count, we give a 180-degree pulse and have them walk back, they'll all end up back at the same place, okay? Pretty boring, but it's actually very interesting because you can put in inhomogeneities in here and refocus those, and that's what the echo has been used for many years. But now let's look at the case where if along the trajectory they start walking away, they may hop and they switch from being a cyan runner and a red runner, okay? So they may not make it all the way back. If you only have one pulse and you have equal time, he may walk this way, and then he walks over here. He switches from a slow walker to a fast walker, and the fast walker can get all the way there. Or a fast walker goes here and switches to a slow, he doesn't come all the way back. So now this line gets broad, okay, because he's not all refocused. Now if you give two pulses and move them closer together, they actually almost come back together, but not quite so much. This line is narrower. That's what that reflects. Now if you increase the number of pulses, you start making them, even though they're switching between slow and fast runners as they go along, they can't get far away. So it's as if you made that process disappear. Okay? So if you now do a set of experiments where you change, you keep the total time that you, from the start of the walk to the end, but you turn them around more and more and more. This is the Carper-Cell experiment. Then you wipe out this exchange. And if you record spectra as a function of that frequency of these pulses, you now get these curves that are called relaxation dispersion curves. So those encode the rate that these are hopping back and forth and how many of them are hopping. Okay? So we have a way of looking at this. And so if there's no effective change or it's very small, you get different line shapes. Okay? And fitting these shapes tells us this. Okay? So how do we measure this? So the Carper-Cell is the classic experiment that does that. And it's analyzed under certain limiting conditions by the Carter-Richards equation, which is, it's not that bad, but it's a little complicated. The key things are the exchange rate, the populations of A or B, you know A, you know B, and the change in chemical shift. This is the offset, how fast they're running. Okay? So you can fit those curves and extract these parameters, but you can only fit them within certain conditions. Okay? And there's a number of reviews, I'll put a few here. And what happens is now you get these very nice decay curves here. And these are for different spins within a molecule. And Lewis has developed experiments where you can measure the nitrogen, the amide proton, the C alpha proton, the carbonyl, and all of these. And so these are curves for the nitrogen, amide proton. That's carbonyl, which you can't see. I can barely see C alpha and H alpha. So you can measure all of these curves within a system that's undergoing two-state exchange. And what that gives you is the rate of that exchange, but importantly, it also gives you the chemical shift of the invisible species that you couldn't see. And the whole development within structural biology is to be able to determine structures using these chemical shifts. So you can actually, using computational systems, understand the chemical shifts. And so these arrows, I apologize, are very light, but you can see between the two states can be very large. And so if you can, this is a case where you can actually force it from A to B, but if the populations are low, you can't. But now you can read all of that out, and you can measure these chemical shifts. And Lewis has used this, and I won't go through the literature that he's done, but he's done this to show a number of very nice studies of interconversion between a folded state, an intermediate state, and an unfolded state, and be able to understand these rates. And that allows you to look at this and understand whether this is going to some disease state, perhaps in an unfolded state, or if maybe this intermediate is an active domain. And this is quite critical in some of the work we do in biological cases that are relevant to cancer, because it's some of the lower populated states that are actually the important states. So, for example, what he's done, and this is just one case where using all of those chemical shifts, you can calculate a structure of the native state shown just as helices. This is actually the ribbon diagram. This is a little easier to see. It's just tubes representing the helices. This is the native state and the intermediate state. You get now it's very different, and so this is actually the state that's critical to function. Okay? So now. I wanted to remind you of that because that's what's mostly in the literature, and Lewis has some spectacular examples of this, but that actually fits in a pretty narrow window of exchange rates between about 200 per second and about 2,000 per second. If you remember the slide I showed you that went from picoseconds to seconds, that's a pretty narrow spot in there. And while these techniques are fantastic, they do have a pretty limited range. So what happens if the rates are more than 2,000 per second? If they're less than 2,000 per second, you come to slow exchange, and that's a different way. There's other methods, and depending on where my time is, I'll say something about that, but we've been interested more in the faster rates because that's governing binding and recognition events. The slow rates, not so much. To get faster than 2,000 per second, we have to do our refocusing very fast. Basically, the CPMG frequency, which is the inversion of the separation of these 180-degree pulses, has to be equal to or greater than the rate we're trying to observe. Well, we're trying to do nitrogen and carbon, and so putting in that many pi pulses on nitrogen at that high a rate usually leads to what we have sometimes called the positive smoke effect. And you will destroy your probe or your amplifier, one of the two. And so you're limited by RF handling and NMR probes. So what do? Oops, there we go. So one thing you can do is instead of doing these pulse experiments, you can do spin lock experiments, R1 rows and R2 row experiments. And that allows you, and then there's some very clever tricks of using off resonance and using effective fields. And the literature is fairly rich from this. I cite one paper from Art Palmer. Art's lab has done a lot of work on this, and they're broken up into schemes, but basically you're putting in, instead of these pulses all the time, you're trying to put in spin locks, where you now have relaxation along a rotating frame. So you're governing the rate of these interchanges based on a new rotating frame, not the Larmor frequency, but a spin lock frequency. This allows you to push this up into the few tens of kilohertz and get around this. Okay? And there is a pretty rich literature about that, and it's also been very successful, but there's a problem, and this is really the problem I want to just give you a new insight into. And that is that, I mentioned in the beginning the robustness of the theory for our effect. One of the problems is to analyze and extract the parameters out of that under these cases is that there are no analytical equations that describe the magnetization under these cases, unless it's under quite limiting conditions. Okay? So we have this problem in general. We can very cleverly devise schemes to send the magnetization through interesting trajectories that will report on and encode these motions. But in order to extract the chemical exchange rates and the populations and the shift, we need some kind of analytical equation to do a normal data reduction. So I'm not going to go into this in great detail, but there's a set of experiments that are a variation of that, and this is largely from John Luigi Veglia and Michael Barwood and co-workers. And this uses these rotating frame R1 and R2 experiments, so spin lattice and spin-spin relaxations in the rotating frame. But now, instead of doing spin locks that I showed you before, that the Palmer lab and others have done, they use adiabatic pulses. And this really came from Mike Garwood, who has been very prominent in the imaging business and using adiabatic pulses to do this. And they developed some experiments that incorporate a series of adiabatic pulses, shown here just as these shapes, just generalized with different phases,
that can be used to encode the same kind of information. And my colleague Frank Chow and I just have a paper that's online in JAX now showing some improvements to this, but in particular how to analyze the data. Because there are some problems in this, oops, let me go here, in the original experiment from the Big League group, there's some problems in how to analyze the data in the same way. There's not a good analytical equation that you can then fit the data to and extract these parameters. So the advantage of this spin lock relaxation experiment using the adiabatic pulses is you can extend the dynamic range that's probed by these. You can avoid some of the need for multiple magnetic field strengths. We suggest 2, but not 4, which has become some of the problems with doing these experiments. We have so many unknowns versus the observables. We've tended to use multiple magnetic fields to gain more data and constrain our fits. We can measure accurate relaxation rates that are independent of frequency offset because we're using adiabatic pulses. For resolution, we want to go to high field, but now we have chemical shift effects. And all of these pulses, this is a problem. So by using adiabatic pulses, we can get around that, and of course we can also reduce the stress on the NMR hardware. So the trick is that this is not only limited to fast dynamics, and it assumes that the original approach assumed that all residues had the same intrinsic relaxations. We can avoid that limitation, and that's what I want to show you. And we go back to the theory, and the two-side exchange is normally described by the Bloch-McConnell equations, the matrix analysis that expresses all the bulk magnetization, how it behaves as a function of R2 and R1, the rates, forward and reverse rates for two-side exchange, the omega-1 fields or the offset fields, and the chemical shift. So all of this information describes the bulk magnetization. And this analysis you can carry out. You can analyze two-side exchange as a wide variance of all of these functions without actually having to have an analytical solution to invert this. Okay? This is valid in the weak RF field limit, which we have in solution, and isolated single spin systems. That only means you need to be able to decouple protons, and I'm not going to go into that, but we dealt with that in the paper that's online. So if these assumptions are satisfied, then the exact solution of this equation is available. You can actually simulate the behavior for all of those parameters. Okay? And so ideally, both fast dynamics and slow dynamics can be characterized by fitting the relaxation data. Okay? Now, the advantage of we use hyperbolic secant adiabatic pulses, and this just shows you some of the behavior of the way the frequency is swept and the amplitude is swept as well. And these are the equations. And this really derives, the pulses we use derive from some work in this paper, which was involved Veglia and Mike Garwood. And what's interesting is to look at how, so we're going to use these pulses in what looks sort of like a Parker cell Meissner-Gill. And what's really clever, and what I think Mike Garwood realized, was that if you look at the trajectory of both the Z magnetization and the transverse magnetization as a function of these different pulses, it has quite an interesting trajectory. And what you see is different amounts of time exchanging between Z magnetization and transverse for these different pulses. And so in essence, by just keeping exactly the same pulse sequence and not extending or causing time, which is an issue for large molecules, we actually encode different amounts of transverse and longitudinal relaxation into the experiment. And through this, we probe this dispersion of relaxation across this. So we keep our time constant. That gives us sensitivity, but we can encode this. And I think this was extremely clever of Mike to recognize. Okay? So what we're able to do is to go back, if you will, to this equation and say, now, the interesting thing is computationally, we can actually analyze the magnetization as a function of any arbitrary pulse sequence because we can divide it into time and integrate in time. And by doing that, we can actually calculate the behavior as a function of the chemical shift offset, the exchange rate, and these pulses for all sets of conditions. And we can create a set of solution surfaces. Okay? And this becomes, in essence, a library that we're going to use to analyze the data. This is the type of experimental data we get from R1 rows and R2 rows, adiabatic cases. And what we can then do is compare the data
against these surfaces. And these are, in essence, 6-dimensional surfaces for all of the data. You can imagine that this is a large computation that takes about 3 weeks to a month to calculate the libraries. And then we do another thing, is what's the accuracy of this? We use something, a geometric approximation. So we calculate those surfaces on somewhat of a coarse grid, and then we use a geometric approximation across the 6-dimensional surface to interpolate and fit in. So we can, in essence, create a basis set with our solution surfaces, and from that, we can then search using the Monte Carlo approach to find the solutions that match all the experimental data across this relaxation dispersion. And by doing that, we can measure the RAX that we measure in an adiabatic R1 row. This is across a small ubiquitin protein. There's a particular mutant that was developed for other purposes that has enhanced motion in places. And we pick up certain exchange rates at residues using the R1 row and different with R2 row. And these are just shown as sort of the size of the sausage, if you will, in the ribbon diagram. What you see is that in the R2 row, the exchange, the REX can be as much as 40 hertz, and then the KEX we can measure up into the almost 100 kilohertz range. Okay? Now, we've applied this to a couple of systems that are large proteins and these ubiquitin conjugating enzymes. And what's interesting is we're seeing rates in the tens of kilohertz range at normal physiological temperature. So this is actually quite fast, but what it means is that these are lowly populated states. And where there's actually large, particularly in this case, in this region here, and then around in this part of the molecule, these are actually regions that are involved in these intermolecular recognition events. And I'm not going to go through all the data, but we go back and look at this. Now that when we put binding partners here, we quench all this motion. So what we're seeing is regulation of recognition by which state is populated. Okay? And we can sample this now directly by looking at these rates, but these rates are actually quite fast. Okay? So what we're able to do using this geometric approximation to solve these very complex trajectories, we do a full analysis to generate the surfaces. We call this the GeoHard. This is the HARD is the adiabatic relaxation dispersions. And we use this, we can probe rates from hundreds per second to almost 100 kilohertz per second. The library only has to be computed once. It's suited for any molecule because we actually computed also for the correlation time. That's a variable. The search to extract solutions is very fast. It only requires a few minutes on standard worktop stations. And if you actually try to, you can do the same process in reverse by numerically integrating those equations as opposed to having an analytical solution. But that's something like 10 to the 5th fold faster to do a lookup. So if you will, you go back to the old days of doing Fourier transform, the Cooley-Tukey algorithm, that's a lookup table, right? So this is really just a lookup table on a basis set of solution surfaces. Now, what's interesting is, and we've already started some of this, you can expand this to look at traditional two-side exchange. Now, that was explained by the Carver-Richards equation, but under certain limitations. We can also expand that to three-side exchange, or now start looking at slow exchange in the CES-type experiments. And analytical solutions are not required, only the ability to solve and compute the full matrix equations. And in current hardware these days, and with a multiprocessor cluster, this is not bad. It does mean that each one of these libraries that you have to compute takes weeks, but it's only weeks once, and then you just download the library, and then you can fit the data. So we're pretty excited about being able to do this. So let me wrap up with just giving you some guidelines. These various experiments. The Carter cell microbial dispersion is great for exchange rates in the 200 per second to 2000s per second. The R1 row, the traditional with the CW field, is good for maybe up to 40,000 per second, but that's really pressing the limits of the probe technology. Whereas the adiabatic experiments can get you up to, say, 90,000 per second, which are very fast rates. And actually, we see this in many cases now, which is very interesting. And then these get modulated by binding events. And you can do this without destroying the probes thanks to these adiabatic pulses and the ability to analyze them. Now, the slow exchange rate I haven't gone into, and I think we won't do that. It's related. these chemical exchange saturation transfer experiments are really for the rates of 50 per second or to 150 per second, and simulations, you know, around 20 per second to this. So this is where it's been applied. And so if you look at this, now what you have using CEST, CPMG, or these, you can now expand, you know, almost 4 orders of magnitude. So that diagram that's very narrow is actually expanding quite largely. And while we apply it only to biological systems, the spins don't care what molecule they're in, so you can use it anywhere. These are available everywhere. And the geometric approximation can allow you to examine this, all these different dynamic modalities. We've showed it primarily for this, but we are applying to the other cases now. I'm going to skip this and just stop so that we can have lunch and go out for a nice walk. I want to acknowledge my friends and colleagues that have encouraged me to use this occasionally, and whether, I don't know whether they like what we've done, but I hope so. Louis Kay at the University of Toronto, Art Palmer at Columbia University, and Mark Rance at the University of Cincinnati, longtime colleagues, and we have great discussions about this. Within my lab at the Structural Biophysics Lab, Frank Chow is the brainchild behind the adiabatic experiment analysis. Michelle Hill, Kalyan Chakrabarty, and Rana Durdas have been involved in various stages of the dynamic stuff. And I'll stop there and handle discussion if you have any questions. I'll leave it there. Okay, thank you.
Thank you for the interesting talk and for reminding us, Professor. Do you have questions?
I can share.
Thank you very much for the first time, for the first part and the second part. I'm wondering whether there is a possibility to combine high field and low field experiments to get a much broader window for observation. I could imagine that this is possible to make it, just to bring everything from the high field where you get a high resolution, to get to bring the system to low field, to allow the system to relax, and then send back to high field to observe.
Experiment. Yeah. I think those are exciting ways to get at this data again. Usually we have to have the high field for the resolution in complex systems. And I think the biggest problem there is just what the actual rates are and whether you can shuttle, I think, physically. I know Al Redfield had built a very interesting system to shuttle. People have kind of not worked on shuttling as much recently. But what we've tried to do is, and because our relaxation rates are such that the amount of the shuttling time becomes a problem for large molecules in solution. Particularly because we're trying to do transverse rates as well. Okay? The longitudinal rates is not such a problem, but the transverse rates. We do feel that we need multiple fields, though, to do this, but those are still all in the high field limit. Okay.
More questions? Yes.
Okay. On one of your slides, you discussed briefly relaxation dispersion. But can you tell me what was on x-axis of these plots?
Okay, so usually so on the x-axis, so the nice curves are from the Carper-Sells. That's the frequency that is the inverse of the how fast you're refocusing.
Oh, I see.
So you have a length.
I saw that it is some frequency, but
it's the, and you control that experiment.
Yeah.
And so there's a limit. You usually can't go much beyond 1500 hertz because of the right. Yeah.
Thank you very much for this interesting contribution, for this nice story. You have described this modified Bloch equation. Yes? My question is it possible to separate, say, spin diffusion and cross relaxation from the real chemical exchange?
It's very difficult, so we include those terms when we do the simulations. So we include all the, well, let me put it this way. If in the full spin system, you have difficulty. So one of the things we do is we try to do the spin system such that we deuterate, we remove the other protons, the general proton bath, and leave it as a two-spin system, an NH or CH system, and then we decouple during the relaxation so that we can handle a single spin system. So we have to worry about that, and we include those relaxation parameters in. It's one of the problems that it's very difficult to invert and just have an analytical solution. But if you include those and you simulate the surfaces, then you've taken that into account.
More questions? Oh, yes?
Very nice talk, thank you. I was going to refer to those magnetization profiles and block Marconi questions. Did you try to account somehow the frequency of the pulses? I mean, this adiabatic pulses. Because if you have low power pulse, the frequency, I mean, the tip angle of the pulse will be dependent on the frequency you want to irradiate. Right?
Exactly.
So, did you account for
Yeah,
it?
so the way the simulations are done is we actually break the pulse into small segments and actually simulate, we integrate across the whole pulse so that we take into effect the amplitude and the frequency and the phase all the way through. That's why it takes a long time to do the library. And you wouldn't do this, you would never do this to analyze one data set. You only do it to have this library that you can then use that's taken all of that into account. Right.
I was just wondering, what is the limit of your 90,000 rate?
What limits it at 90,000? Well, I'm not certain I believe our error rates when you get past that.
Isn't it pulse length?
Well, yeah, pulses are a problem, the total length.
The sample is a different one at the end of the pulse. Right?
Yeah. Because so we're doing about, we do 4 pulses and they're 4 milliseconds each, so we have 16 milliseconds across them. Yeah, and we have, and you're right, if we try to do that in a different way, we start coming into the other problems. We can handle that in most cryo probes. I think we could probably build a probe that would not be a problem, but in the sort of biological arena, that is a limitation. You're right.
No more questions, so please thanks both speakers again.